All right, here we go. Today is Thursday, May 3rd, 2012. I'm actually recording this on Monday, but I didn't have a chance to do it Thursday because I was videotaping the lecture for the weekend. So today what we did was we checked over the concentration calculations worksheet. Today, things that we're going to work on those questions for the concentration problems, which there weren't that many. So I'm guessing that that's easy. We're going to talk about titrations today because next week we are doing a virtual titration, next week we're doing real titrations in class. If you're not in class, you're going to wind up doing a virtual titration instead. That link will be on the blog later on. But basically tonight, actually, before we even leave class today, we got the titrations worksheet done. The titration problems really aren't all that hard. So let's get straight into it. Basically, what a titration is it's an experiment that's designed to determine the concentration of the known volume of an acid by neutralizing it with a measured volume of a base that we do know the concentration of. So basically, what we're talking about here, that was a joke, little acid-base joke. But basically, what's going on here is that we take an acid and we put it into an Erlenmeyer flask or a beaker, as well as an indicator. We typically use an indicator like phenolphthalein that changes color when the acid has been neutralized. Okay. Then we fill up what's called a burette with a base. You can see that a burette is a device that has very precise measurements, judging from the number of lines that's on it, so that what you can do is you can measure the volume of base that you use to neutralize this acid. Now, I know how much acid, so I know my volume of my acid, okay? And it turns out that if I know the molarity, if I know the concentration of my base, I can figure out what the concentration of my acid is relatively simply. So I know this, and I know this. I want to calculate molarity of the acid. Hey, I've got a 4-variable equation where I know 3 of the variables. That's easy math. Okay. So ultimately, what this looks like, we've got our nice burette here, and we've got our acid, our unknown concentration of acid, along with a little bit of phenolphthalein in there. We drop in some sodium hydroxide from up here. This is exactly what the lab is that we're doing in class. Sodium hydroxide, which is 0.2 molar. Okay, and this is HCl of an unknown concentration. Excuse me. Got the hiccups today. All right, so what's going on is we add a few drops of the sodium hydroxide in, and what you see down here is that the solution is going to turn pink. As we swirl it, it turns back to clear. So we add a couple more drops of sodium hydroxide, it turns to pink, and it continues to turn clear. When we're getting real close to the end point, it's going to take longer and longer for it to turn clear as we're swirling it. So we know to slowly go dropwise as we continue to go, because we really don't want to overshoot. If we overshoot, it's going to turn dark pink immediately, and we're going to have to start over. If you get really good at this, you put 1 drop in at a time at the end, and you get this beautiful light pink color. That tells you hit your end point exactly precisely on. And at that point, all it's a matter of doing is just plugging into the equation that I just showed on the last slide. Molarity of the acid should be, if I rearrange it, equal to the molarity of the base times the volume of the base over the volume of the acid. It's going to be that simple as a rearranged equation. I don't think I showed this rearranged equation in class, so don't tell anybody. All right. So here's our equation here. MAVA equals MBVB. And the problem that we've been given, 20.1 milliliters of a 2 molar sodium hydroxide is used to neutralize 10 mils of HCl of unknown concentration. What is the concentration of the HCl? Okay, so pause the video for a moment and write down what needs to be done and even solve it, okay? Okay, so as you suspected, we're going to try and solve that now. MAVA is equal to MBVB. So by that means, what we've got here is it said that we had 20.1 milliliters of the base was being used. We've got MB, which is, let's see, the molarity was 2 molar. It said that we had 10 milliliters of the acid being used, and we don't know the molarity of the acid. Algebra takes over here. 2 times 20.1 gives us 40.2. M times 10 is still M times 10. We got to get rid of that 10 on that side because we want M by itself. So it turns out that the molarity of the acid is going to be 4.02 molar. Okay. Now, if we're looking at sig figs here, technically this was called 10 without a decimal, so I guess we're only really going to know this as a 4 molar. Technically, a measurement like this should be done at least in the 10th place like that, so it should be 3 sig figs. So I would expect that in real life, if we were doing this, say, next week, that you'd get 4.02. I'm sorry, this is our virtual simulation of what's going on. We're going to pick strong acid versus strong base. Fill the burette with, well, we like to fill the burette with a base. We're going to use the acid hydrochloric and the base sodium hydroxide. We will pick the indicator phenolphthalein. Let's see, what do we need to do next? That was 4, so 5, push the slider up to add a volume of base. So the next thing that we do, you can see that they set us up here. They tell us we have 25 mils of acid, and we have a molarity of 0.1423. So we could add dropwise, and we are going to be here practically forever, because this particular burette looks like it can give let's see, 0.02 milliliters at a time. So what I'm going to do is I'm going to add a whole bunch in. All right. There's 10.18 milliliters in. Haven't seen it turn pink yet. 15. Oops, it turned pink. Just for a moment there. If you watch down here, you see it's going to turn pink as we add one more drop. There's another drop and another drop, and it's turning pink just slowly. I'm going to see if I can boost this just a quick. Oh, you know what? I might have overshot it. 18.78 is possibly too much. So what I'm going to do here is I'm going to hit concordant values. Basically what this says is let's empty out the beaker. Let's get a new 25 mils of acid. And we're going to use the same molarity of the acid. So let's see if we can do that again. What was it, 18.42? So I'm going to try and put in, oh, I don't know, let's put in about 17. There we go, 17. And it hasn't turned pink yet. So we're going to hit it drop-wise. Very slowly. Notice that might have been just what we wanted, 18.42. Slowly, slowly, slowly. Getting a little impatient here. Perhaps if I understand the video editing software, I can fast forward this part. Looks like 18.42 might have been pretty gosh darn close to what I was supposed to have. 2.2, 18.3. Four, 6, 4, 7, 4, 8. Gonna be too long. Okay. See you tomorrow. Oh, there we go, right there. 18.74. Notice it, one drop changed it completely pink. So I'm going to take 0.1423 on my calculator, multiply by 25, and then I'm going to divide by the amount of base that I used. According to this, it's 18.74. Divide by 18.74. My calculator tells me that the molarity of the acid is 0.1898. Let's see, I'm going to round that 190. And we're going to click OK here. There we go. We got it correct. And we were shown that that is absolutely correct. So we feel good about that. Let's see. Shift back to the PowerPoint. Here we go. Okay. I would suggest at this point, since you've seen what a titration looks like, and we've done a couple of problems, I would suggest you go ahead and pull out that worksheet, the titration problems worksheet, and work out the problems, and press pause for a moment, because next screen you're going to see are the answers. There's the answers there. Now, I highly suspect that you're not going to have had any problems anywhere with any of those answers except for problem number 5. So as you're double checking, what you want to do is you want to look closely at number 5 and see what it is that makes number 5 different from 1 through 4. Take a careful look at the acid formulas. If you looked closely, what you'll have noticed is that the acid formula for problem number 5 is different because acid number 5 is a diprotic acid. There's 2 hydrogens, whereas all of the other acids had 1 hydrogen. That was done on purpose. The reason for this is the reason for the fact that your answer was 0.01, exactly half of what my answer is that you should have realized that H2SO4 being diprotic means that it has twice as many hydrogen ions to give up than hydrochloric or hydrofluoric or hydrobromic acid. So its effective concentration as an acid is actually doubled because of that. Okay, so the molarity of the H2SO4 molecule is only, well, it could be only 1 molar H2SO4. If I had 1 molar H2SO4, that means I've got 1 mole's worth of 2 hydrogens and 1 sulfate in solution. But what happens when I put this in solution is that it ionizes completely because it's a strong acid. So I get a hydrogen ion, and a sulfate ion. What are my concentrations for my ions? Well, I've got 1 molar sulfate because there's 1 mole per liter of sulfate and the sulfate comes out. Now there's 2 hydrogen ions. Each is 1 molar. So that's 1 plus 1 equals 2 molar of the actual acid components, which is the hydrogen ion. All right, so that's why you get twice as much. So you've got to be careful on problems to see if you've got a diprotic or even a triprotic acid. Let's see the famous triprotic acid, H3PO4. Okay.